My name is Huseyin. I'm a professor of mechanical science and engineering at University of Illinois at Urbana. My graduate student is Samir Mohammed. The title of my presentation is Type 2 Twin Interface and Evolving Identity. The work is supported by AFOSR with Dr. Ali Sayer as the program director. Twin boundaries are fundamental interfaces in material science which continue to surprise us. A long-standing anomaly in the field is the experimental observation of type 2 twin boundaries with several distinct identities. The nanostructure of this boundary is still unclear. We consider multiscale energetics to establish a Terrace-Disconnection topology of this interface as an energy minimal nanostructure. We're developing a theoretical framework based on continuum strain energy arguments to determine the influence of external strain on this interface. And we find that this topology evolves across a continuous spectrum of indicial identities depending on the external strain. We point out the nature of this interface with defect or dislocation spacing, which can change depending on the applied strain as well as the type of interface we have. We consider not only type 2 twin interfaces, but also type 1 and compound interfaces. We show that the dislocation densities of this interface can vary by an order of magnitude, and this has ramifications in understanding the reversibility of transformation, reversibility in twinning, as well as in understanding in hysteresis in these materials, as well as fatigue in these materials. Now, we want to show a micrograph of this interface, which is shown with this dashed line here. This is a high resolution image. We note immediately that this interface is somewhat diffuse. It's not appearing as a sharp interface. It is close to the 1-1-1 plane, but it's not exactly on the 1-1-1 plane. It deviates from the 1-1-1 plane. This structure of this twin boundary is the topic of my presentation. It exists in various functional materials. As I point out that precisely this boundary affects the irreversibility is observed in the transformations such as development residual strains, residual displacements, and influence of the performance of all classes of functional materials. If we look at textbook examples of twins in face-centered cubic materials or body-centered cubic or hexagonal close-packed materials, they exhibit all a very sharp interface. This is a schematic. If we look at high-resolution images, such as in silicon, we also see sharp boundaries. And also in hexagonal close-packed materials, there's a distinct crystallographic plane. On the other hand, the type 2 twin boundaries are irrational. They are not on crystallographic planes. And we want to understand why this happens and what's the ramification of this. So no consensus on the structure yet. We're considering martensitic crystal structures here that are undergoing twinning, low symmetry materials. This is a monoclinic crystal with crystal lattice axis ABC and monoclinic angle beta shown in here. The definition of a type 2 twin boundary is a 180-degree rotation around the 0-1-1 axis. as shown here. So this is a mirror symmetry across the twin boundary here, as shown. Away from the boundary, there's a perfect mirror symmetry, but at the boundary, there's a defect structure that needs to be understood and evaluated. There's an ongoing debate on the nature of this type 2 twin boundary. And most of the previous work was experimental. Recently, there has been modeling work. 2018, 2019 by Pond and Hurt and Knowles. These are senior prominent people in material science, and our work as well, which I'm going to discuss today. Now, the first question we need to address is what is the formation mechanism of the type 2 twin boundary? And in the Pond and Hurt treatment, they postulate that dislocations actually glide on a type 1 plane, 011 plane, and form a tilt wall structure. Now, they describe this twin boundary, type 2 twin boundary, as a tilt wall, TW, tilt wall structure. Another proposal is that dislocation glide occurs along the nearest rational 111 plane, and the step geometry develops at the boundary. So this step geometry is called a disconnection. So this dislocation here with a step character is called a disconnection. And there are terraces on the 111 plane with steps. And in this particular case, the orientation of the dislocation and the misfit strains, internal strains, are different than the tilt wall case. The question is, which structure is optimal from an energy standpoint? The Terrace-Disconnection structure or the tilt wall structure? So we undertook some calculations which have not been done before in the last year. We did these calculations determining the continuum strain energies associated with these dislocations, as well as the atomistic potential energy, accounting for the core of these dislocations. And we find that from a continuum standpoint, at a first glance, the tilt wall structure has a lower energy, 0.5 microjoules versus 0.5 millijoules. But the atomistic energy, potential energy that we determine is far smaller in the Terrace disconnection case compared to the tilt wall case. And this value of energy is much higher than the continuum energy. And consequently, we determined that the Terrace disconnection model is more favorable. Reason why there's a difference in the continuum energies is because in the Terrace disconnection model, we are accounting for the mismatch strain at the interface, a mismatch in shear across these two variants, which can only be accommodated, or the internal strains can be relieved by the presence of these dislocations at the interface with spacing d. And this produces a higher continuum energy. But from the atomistic point of view, the arrangement of the atoms in these two cases is drastically different. And the atomistic energy dominates the decision, the final result. So we recall the background. We're showing these results of the previous cases of perfect boundaries, and we point out that because of this Terrace disconnection with dislocation spacing, which is finite, we're getting these internal distortions in the material. And that's why the high resolution images do not show a sharp boundary, because there are internal displacement associated with these dislocations. We point out that the D infinity case, where these dislocations are way far apart, is really the pristine boundary where you have only terraces, but no steps. And the proposed twin advance for this mechanism is shown here. So this stepped interface moves, and one can grow the variant, one of the variants with respect to the other. So the twin partial advances, and then the twin growth occurs. It is difficult also to visualize how the twin can grow readily in the case of a tilt wall configuration in this particular case, because it's not obvious how these dislocations are going to move in that case. So we summarized our findings so far. There is another issue that we decided to address, and that is to do with the fact that this type 2 twin boundary have different indicial identities in the literature. So there is the Nishida's work, which shows that the boundary is about 10 degrees from the 111 plane, while Zhi and Liu shows that the boundary is about 5 degrees. And so the planes, the twinning planes are different, 344 versus 899. It has two different experimentally determined identities. What we want to show or understand why this anomaly develops. So in the case of 344, the dislocation spacing at these interfaces is quite small relative to 899 case. And so the dislocation glide or slip can change this identity. We wanted to explore the role of external strain. So if we look at the applied strain effect, it can influence the determination of this dislocation spacing. This is the mismatch in the displacement gradients, displacement gradient jump. This is the traction continuity across the terrace plane. This is the average microstructural strain. This is the external strain applied, which is not present in regular calculations, which we introduced. And the energy minimization here incorporates the spacing of these dislocations. So we undertook these calculations to establish the role of external strain on the type 2 twin boundary plane, and we show that the current experimental findings can be reconciled based on the role of external strain. And if we look at the type 1 twin or compound twin, they also exhibit a change in strain. The boundary deviates from the zero strain case, but the sensitivity in type 2 is higher. There's also sensitivity of the volume fraction as shown in here. And so we extended this topological modeling framework that's normally done for zero external strain to finite strains. And we established that the dislocation spacing depends on the presence of strain. This is the zero strain case. This is, in this case, minus 5%. And clearly, the spacing is different in these two cases. There are some implications of these results for transformation, reversible transformation or fatigue. As we know, these dislocations are emitted at these twin boundaries to the austenite, to the matrix, and that's experimental results shown here, the emission of slip into the matrix from the Martin side. And we note that in the case of forward and reverse loading, the dislocation density at those boundaries is not the same. So the Berger's vector summation in the forward case and in the reversed case are not the same. So that differential produces a net production of slip into the matrix, which is what one observes in these experiments. So if it was fully reversible, forward and reverse, then there wouldn't be any dislocations in the bulk of the crystal. But these dislocations are emitted because of the unbalance in the dislocation density content in the case of forward versus reverse strain. In the case of positive strain, back to zero strain. So in summary, we point out that this differential is responsible for the buildup of dislocations or slip in some of these transforming materials. We're further working in this topic at the moment. In conclusion, we want to say that type 2 twin boundary structure is addressed. There is a energy optimal Terrace-Disconnection topology, and it evolves its identity, and we resolve the long-standing experimental disagreement that currently existed, showing why there is a difference in the findings of various experimentalists. And we proposed a hypothesis for slip emission in shape memory alloys, as well as in other transforming materials, based on evolving of this twin interface. Thank you.